See you speaking again. Today we are going to walk a bit backwards until we'll be able to identify the two guilty guys I want to talk about. Let's start it. Here is the project we've seen last time, where imagine there is a process working for 35 seconds, and after every 35 seconds, there is a big red light. Now I modify the project a bit. So the big red light, which is going to stay on for about 10 seconds, and everything goes again. I disconnected the alarm, the audible alarm, so you won't hear it unless I'm going to push the manual reset. So the automatic reset goes as before, as it happens now, but the manual reset goes together with the alarm. So by doing this, we're going to pick up just the flashing red light to take our measurements instead of a multimeter. And we're going to use measurements first, and then we're going to use our measurements to figure out what happens. So it's going like this. Instead of using the red light, like right now, figuring after 35 seconds a reset of 10, I'm going to disconnect the red light, and I'm going to connect this wire right here on the blue line on the ground. What happens is I'm referring to this particular package, which from the list here is exactly this one, 4584, is a CMOS package containing, as you can see, 6 inverters. And the inverters are arranged exactly the same way in all the packages I put here. You'll find this one as usual on Google Drive. So the package, you see the notch, and from the notch, the pin number 1 is right here. So there are 1, 2, 3, 4, 5, 6 inverters. And for the purpose of our project today, what we're going to do is we're going to pick up the output of the first inverter and link it to the input of the next. It is exactly the little jumper you can see over here. I'm touching it with my pencil. We're going to do the same between the pins 4 and 5 right here. So if we move, we're going to link these two together. So it's like we put in series 3 inverters right now, but we cannot say we put them in series like resistors, because the inverters apparently are in series input output, and the output becomes the input of the next, and the output becomes the input of the next, and so on, simply because there are also 2 extra wires you can't see, the ones energizing the inverters. So the operation we do right now, we call this cascading. Cascading what? Inverters. So we're going to cascade. So now I'm going to go even further and picking up a wire from here and going on the top of it and linking this output pin number 6 to the input number 9. And I'm not going to pick up all of them, 5 out of 6. I'm picking now the pin 8, which is an output, and linking it to the input of this one. So the last output we are going to use is going to be this one. In other words, we have cascaded 1, 2, 3, 4, 5 inverters. And now, let's suppose for the first version of this little practical project, we connect the input of the first inverter, which is exactly this orange wire, from the pin 1 to the ground. Why to the ground? Because remember, the ground is representing for us in binary the 0 logic. So now I'm going to write it here. Let's suppose the first value was here a 0 logic. If it is the case, then this wire I pick up driving the red light, the red flashing light. If I'm touching here on the same pin 1, nothing is going to happen. Why? Because my input is connected practically to the ground. So this is why it's 0 logic. But when I move it at the output of the first inverter, which is the pin 2, I'm doing it right now, the light starts flashing, meaning it's like the light is energized. So it's becoming a 1 logic. which is absolutely normal because, as you can remember, this is what the inverter does. Whatever the input is, the output is out of phase 180 degrees. Exactly like if you imagine here a circle, and here is the position for the 0 degrees. I'm talking about geometrical or electrical degrees. And here is the position of 180 degrees. While the input is at 0 degrees, the output is at 180. So they are out of phase 180 degrees. This is why we have an inverter. By the way, regardless what direction you take for this measurement. But now, the pin 2 here, I connected my red light to. I'm moving it on the pin 3. And obviously it's the same because the output 2 becomes the input of the next inverter. What's going to happen? Because I'm going to write it here. This is still one logic because you can see the light on flashing. I'm going to move it on the next pin, which is the pin 4. As you can see, the light is off. So I'm going to write here a big 0. The 0 transfers here at the input of the next inverter. What do you think you're going to find on the pin 6 and 9? Pin 6 and 9 are right here across this piece of wire. So pin 6 is right here. So on the pin 6, you're going to get a 1 logic. And on the pin 9, if I'm moving it right here, you're going to see the same, a 1 logic. So I'm going to transfer this 1 right here, 1 logic. What do you think is going to be on the pin 8 and on the pin 11? I'm just moving it 1 hole away on the pin 8 and on the pin 11, right here. Sorry. So this is going to be a 0 logic. 0 logic here, and it's going to come here as 0 logic. What do you think you're going to find on the pin 10? I'm just moving it on the pin 10, is right here. Is a 1 logic. So we established the first set of measurements. Now, we're going for the second set of measurements. I'm moving this wire at the input on the pin 1. I'm moving this wire here to the positive voltage. So, in that situation here, I'm going to pick up my wire from here back to the pin 1. But now, because the pin 1 is connected to the positive voltage, this is why you see the light on. So I'm going to put this with another color. If this first terminal is connected to the 1 logic this time, what's going to happen here on the pin 2? On the pin 2, you're going to see a 0 logic, which is absolutely normal because before the input was a 0 and the output was opposite to it. Now the input is 1 logic and the output still has to be opposite to it because we still face an inverter. And the same is going to be on the pin 3. Absolutely obvious. The 0 comes here. What do you think is going to be on the pin 4? The light goes back on. So it's a 1 logic. What do you think is going to be on the pin 5? Of course it's going to be transferred here. It's a 1 logic. What about the pin 6 and then pin 9? Right across this little piece of wire. So we put it here. It's a 0 logic. And obviously right here a 0 logic. What about the pin 8? Oh, the pin 8 is going to be right here. So the pin 8 is going to see clearly a 1 logic. And this is going to go on the pin 11 as a 1 logic. And what about the pin 10? The pin 10 is right here. So it was a 1 logic. The pin 10 is going to be 0. What about these two sets of measurements? What is the purpose of all that? Take a look what it is. Right here, we found out that regardless if the value of the input is a 0 or it is a 1, the output is going to be always opposite to it. If it was a 0, it is a 1, the output. If it is a 1 at the input, the output is 0. And so on, everything goes like that. Regardless how many inverters you cascade one after other, they're going to respect that rule. Now, how do we write it mathematically on the paper? Because on the electrical diagram, we understood some time ago that we just put here a bubble, and that bubble represents the symbol for the inverter. But let's suppose we're going to give a name to that input, and we're going to use a letter, A. Mathematically, the notation for the inverter right here, for the operation which is inverting, is the same letter A as before, but we put a bar on the top of it. That bar in the top of it means instead of being here, we were at the beginning, we're 180 degrees out of phase, shifted here. So the notation for the inverter is this. So keep in mind, anytime you pass an inverter, whatever was at the input, it has to receive a bar in the top. So right here, if this is transferred over here, it's going to be the same letter A with a bar in the top. What about the output? Whatever was at the input, which was this thing, is going to receive a bar in the top. So now, take a look. We have the letter A we used before, but instead of having one bar, it has two bars. But take a look. If it was a 0 right here, it is a 0 over here. If it is a 1 here, it is the same 1 over here. So what you can conclude is that one of the first rules we already have is that A is equivalent with A with a double bar. So in other words, after you pass two inverters, what's going to happen? The first inverter goes from 0 to 180 degrees. And then from 180 degrees, you go another 180 degrees and you reach the same position as the 0. So the 360 degrees is on the same position as the 0. This is exactly what happens here. So the actual difference between the two inverters is just the duration it's taking for the signal to pass from here to here, which is very short, nanoseconds. So let's pick up this one and go further. We go from pin 4 to 5. We have the A with double bar. But when you pass here to the pin 6, whatever was at the input, which was exactly this, it receives a new bar, because a new bar means every new bar means an inverter. So take a look. From the first input here, you have one bubble, two bubbles, three bubbles. And this is why you have three lines. But if you take a look over here, this one and this one are the same, because this one and this one are the same. So a second rule here is going to be this. A with one bar is the same as A with 1, 2, 3 bars. Why? Because we've seen this already. The two bars, every two bars, they cancel each other out. So if you cancel these two out, you remain with one bar, which was exactly this one. So this whole thing goes further. And if this one goes here as A with 3 bars, it's going to become here A with 1, 2, 3, 4 bars. And this one comes here with A 1, 2, 3, 4 bars. It's going to come here as A with 1, 2, 3, 4, 5 bars. So A with 1 bar is the same as A with 3 bars. And guess what? It's going to be the same with A with 1, 2, 3, 4, 5 bars, and so on. In other words, here you have odd numbers, and here you have even numbers. So any even number of bars is exactly the same as the letter or the input, whatever name you give it, with no bar at all. And any letter or any name you give with the odd number of bars is equivalent, finally, with the letter or the name with only 1 bar. Now, I used this little project with the inverters just to tell you who put this at work for us. How did this appear? Because on the diagram, there was a bubble you could put, but when you write a mathematical equation or a formula, you have to put a symbol. So the symbol used with the bars. So we have to return back in time somewhere in 1937. There was a very brilliant student amongst so many others, Claude Shannon. So Claude Shannon, I'm going to write his name here. Claude Elwood Shannon. In 1936, he had a double degree from the University of Michigan in electrical engineering and in mathematics. And in 1937, he went to MIT to get his master. And imagine this, the thesis for his master, which is about switching circuit theory is considered till today by the most scientists around the most important thesis in electrical engineering ever. So this guy actually put the foundation for the logic circuitry we use today. However, when he did this, and he started actually to work on that while he was still at Michigan, at the University of Michigan, he needed a kind of theory to, let's say, support his own. And the mathematical background he needed was suggested by one of his old professors. You know what? You are working on a very complicated thing to improve the circuitry of the relays in the telephonic centers. And for that, it's very complicated because some of these relays, they may have more than 100 contacts, and they were not very reliable back in the 30s of the 20th century. Maybe for your theory, you should look for a name, for a forgotten name in mathematics called George Boole. I'm going to write his name here too. George Boole. Now, I mentioned here the name 1937, when Claude Shannon wrote his thesis about switching circuit theory. And George Boole wrote his most famous paper about a very special kind of mathematics somewhere in 1854, almost 80 years earlier. Because the guy was too much ahead his time. I'm talking about George Boole. When he died, everybody forgot about him very quickly. Maybe just a funny thing about how he died. It wasn't funny for him anyway. He had a very fragile hereditary background, or if you want, he was very sensitive with his lungs. And one day he forgot his umbrella at home, and being a professor at the university in the county of Cork in Ireland, it was raining cats and dogs. It was raining very often. So this day it was a rainstorm. And the distance between his house and the university was about 3 miles. And the rainstorm started somewhere in the middle. So he preferred to reach the university because he didn't want the students to miss his lecture. But he stayed the whole day at the university without changing his clothes. And when he reached home in the evening, he fell ill. So he caught a pneumonia. Just to understand how quickly it happened, he caught a pneumonia on November 24, and he was gone forever on December 8th, 2 weeks. One of the things maybe contributing to his sudden death was the fact that his loving wife, he married in 1848, Mary Everest. He was a niece of Sir George Everest, whose name was given to the mountain. And his loving wife, to not digress, was adept of a new kind of discipline, homeopathy, who just appeared. And the thing was to fight against the disease with the same means creating that disease, but in small dosage. So he put the poor guy under blankets in bed, and gently, as a loving wife, he was spreading from a bucket water, fresh water over him. So this is why it didn't take too long before the guy was completely gone with the pneumonia. Okay. Anyway, returning back in 1937 with Claude Shannon, when he discovered the theory, the mathematical theory used by George Boole so many years ago, almost 80 years earlier, he realized, hey, that's solving all my problems about the mathematical foundation for my relays. So for that reason, the mathematical calculation we used last time in the last video for the OR gate and these new things today for the inverter were actually put on the paper for the first time with no integrated circuits. How many computers were there in the 18th century? But the mathematical calculations were put on paper first time by George Boole. This is why we call this kind of arithmetical things Boolean algebra, or if you want, logic algebra, which is completely different from the standard arithmetical calculations we do on our pocket calculators. One last mention for today is that Claude Shannon, you can consider, like so many scientists in the last 10 decades, if you want, almost 10 decades, that this is the most important genius you've never heard of. Because he did so many things in his life. He got all the awards an engineer can imagine, except the Nobel Prize, because his discipline he was playing in, the information theory, like the control theory governing the PLCs, for instance, there's not a discipline for the Nobel Prize. But he's considered on the same pedestal with Einstein, and he personally knew Einstein, by the way, on the same pedestal with Einstein and also Sir Isaac Newton for mechanics. Each of them in his field, they are considered pairs, So, two guys to recall for today: Claude Shannon, who rediscovered George Boole, and of course George Boole, who wrote the foundations for the mathematical calculations we use in all computers today. Thank you very much for today. See you next time. Bye-bye.